Dr. Barry Sanders. We have great honor to have him today with us. And there is no need to much say about him because I think he's well known all over the world, including US. So he's currently director of the Institute for Quantum Science and Technology at the University of Calgary, a 1,000 Talents Chair at the University of Science and Technology in China, and visiting faculty member of the Raman Research Institute in India. His bachelor degree was earned at University of Calgary in 1984, and he got also a diploma from Imperial College London, where he received PhD in 1987 from Sir Peter Knight. So he's been at University of Calgary since 2003. So he's going to talk today about topological quantum dots, theory and experiments. Quite exciting academic subject, and he's of course known for contributions in many other fields of quantum information and quantum computing, which you can find going through his sites that are quoting him, and especially a mile of his papers. So he's currently chief editor of New Journal of Physics and past editor of several other international journals. So, Dr. Sanders, please replace me.
Thanks. So thanks for the very kind introduction. It's a great pleasure to be here, and I'm grateful to Vladimir Korpin particularly for instigating this visit so I could come here. I'm giving this talk today, and then I'm also speaking again on Monday, so I'm around for a few days if anybody wants to meet and talk with me. So this talk actually I'm giving for the first time today, so I haven't done it before, so I apologize in advance if it's not polished, because as I read the slides I might get a little bit surprised. And as is the custom in my group, my students prepare. So we spend like days preparing. They prepare, so all the slides were done. My student didn't put his name down. Jijo, his name is Jijo Wu. So he prepared them, and we've been back and forth. So now I'm going to see some of these based on my last comments. That's it. I find it good, actually. It's good for students to prepare the slides. It trains them. So I should say I'm sorry I'm lazy, but actually I'm saying I'm proud that I'm getting my students to work. Okay, and so I'm going to talk to you about topological quantum walks. It's kind of growing, and I need to explain to you, and I was told to be basic, which is good because I like to stay basic. So I'm going to try to explain to you exactly what it means to have quantum walks. And I've been working in the field since the start. So this field's been around for almost 20 years, and I'm still trying to understand what I mean by the term. So I'll share that idea with you. Actually, so as you heard in the introduction, I have a few jobs. And one of them is at the University of Science and Technology of China, where I joined a few years ago as a 1,000 Talent Chair. And this is work I do in China, not Calgary. And it's interesting to be here because right now there's all these controversies, same Canada and the US, about the connections with China and all the rest. And I just want to say I'm very proud to be in that position. And I'm very happy to help with the advancement going on. So it's primarily the work I'm doing in China that I'll be talking about. And then I'm also at the University of Calgary. None of this is related to my job in India, so I didn't put it down. And then, yeah, so I'm working editor-in-chief New Journal of Physics, and I'm also a senior fellow with the Canadian Institute for Advanced Research, which also funds me. So those are the affiliations. Okay, that used up to a lot of time. Okay, so and here's the Shanghai, and this is Calgary, so you can see the two cities I'm based in. Okay, so I'll just give you an introduction to the field. I'm going to talk about just the ideas of quantum and topology together, and then I'll specifically get into topology and quantum walks. And then recently I've had the pleasure of collaborating on projects to do with PT symmetric quantum walks. So the PT symmetry is a you change the axioms of quantum mechanics. The way I think about it is there are other universes out there. Our universe has quantum mechanics. There might be some other universe that has this consistent PT symmetry. And so we simulate this PT symmetry in our universe. So I'll talk about this. All these things are both theory and experiment. So I'll talk about both. And then I'm going to give you some tentative results. And so you'll see that some things I mention are related to Chern-Simons theory and spin-1 chains and stuff that people aren't experts here. So the reason it's the first time I'm giving this talk is because the results aren't finished. So I'm going to tell you what we're trying to do and where we're stuck. And then I think that there's a lot of smart people in the room who might see something that my small thinking isn't able to grasp. So I'm kind of doing like a workshop model where I'll tell you where we're at, where we're stuck, and I think anybody with a good condensed matter background will see things I don't. Okay, so then I'd like to just start off and tell you right away what the point is. So if you want to go to sleep or anything, at least you know what you'll miss. You get the idea what the talk's about. So the idea here is really to employ the tool of quantum walks, and this is to reveal topological properties. And I'll explain what quantum walks are. But the purpose of this talk is really, there are topological effects that go on. Quantum walks are a very beautiful approach to dealing with quantum mechanics. And so we want to deal with this beautiful approach and explore topological effects in that way. Not just rewrite what everybody knows, but to use quantum walks as an approach to try to make new discoveries and especially to do experimental simulations. So what we've been able to do so far, both theory and experiment, is the quantum walks are generated by a Hamiltonian. We're able to vary these Hamiltonians. We have worked out topological quantum numbers that are meaningful in experimental situations. And we calculate and experimentally show, through looking at this walker, this quantum walker, again I'll explain, what the walker is doing, and the walker's behavior is revealing directly to us what the topological features are. And we use that to characterize topological phases and phase transitions. And why is this important? Well, it turns out that by thinking of this as quantum walks, I think that we're thinking of new ideas. And one of them I'll talk about is to go into generalize internal degrees of freedom, internal symmetries, in order to search for more exotic topological phases. So that's what I think is the most significant part of what we're trying to do. And you can judge for yourself how close we get. Okay, now I'm going to give you a bit of a history lesson. So I feel that most of you haven't heard of quantum walks, I guess. It's nice to just start from a historical perspective. So I thought I would just tell you, there's a paper here by Yakir Aharonov of Aharonov-Bohm fame, 1993, Physical Review A. Oh, by the way, I put down, you know the DOI for papers, Digital Object Identifier. Just like there's URLs that are short, Google, Bitly, and so on. DOI runs a short version. So if you ever want to record it, if you just write down up to 6 characters, plug it into the DOI service, you'll find it. So it's just a quick way of, if any paper looks interesting, just record these up to 6 characters and you can find it through DOI. So Yakir Aharonov, others, Louis Davidovich, and I forgot the third name, did work where they said, okay, let's take the random walk. So the random walk is ubiquitous. It's used for Brownian motion. It's used in computer science for solving problems like 2-sat. In mathematics, it comes up in the Wiener measure was created to deal with that, Ito and Stratonovich calculus, and so on. And so they just said, how would we do it quantum mechanically? And so the idea is the following. So if I take a coin, so if I'm a walker and I want to do a random walk, I flip a coin. If it's heads, I go right. Tails, I go left. And then you look at the distribution. And so if I'm standing here as a delta function, over time I spread out as a binomial distribution that approaches a Gaussian. And so that's the way the random walk works. It describes diffusion and Brownian motion and so on. So that's the idea. You can just think of it generated by a walker flipping a coin, and then you get this stochastic behavior that if you do it over and over, you'll build up a Gaussian distribution. So that's what's going on. So these guys gave the walker a quantum coin, and then, so the coin could come up a superposition of heads and tails, then the walker going right or left is entangled. Right is right, coin heads step right, coin tails step left, and then do it again, keep flipping the coin, and that's what they studied. They managed, I'm sorry to say, they managed to make it very uninteresting. The paper's not well known because they proposed performing a measurement at every step to build it up. So what you see here is the Gaussian wave packet stays Gaussian, it gets a little bit broader, and then it's just moving around is a diffusive process. If they didn't measure every step, they would have seen more interesting things, but that's what that paper was in 1993. Then what happened was the computer scientists didn't know about this, but some computer scientists around 1999 started to study quantum walks on graphs. So they were thinking about the following, that the random walk is an algorithmic tool to solve a problem known as 2SAT, which is, it's a Boolean satisfiability problem, but satisfiability problems underpin optimization problems. So if you do optimization and you want to boil it down to basic algorithmic ingredients, random walks are important, an important tool to be able to solve. And they started asking whether, this is about 1999, so the Shor algorithm was out in 94, Grover search about 96, and so people were really getting hot about finding new algorithms, and they started looking at this. And there were two different groups, and in computer science, I think this went to Stock's Symposium on the Theory of Computing, and in computer science, if similar talks come in, they forcibly merge it. So this was a merged talk between two different groups, and they studied the quantum walk on the graph, and basically they were looking for speed ups and hitting times, various things I won't go into, but this is kind of what happened. And then there was more work that went on. This was going on the theoretical side. There was some work by my former postdoc supervisor, Jared Milburn, and his student. And the same year, I did some work with Peter Knight and some others. And so they looked at how to see the quantum walk in an experimental ion trap scheme. We looked at it in the context of Serge Haroche's experiments. You might know Haroche got a Nobel Prize for sending atoms through a microwave cavity. And at the time, he told us that he was trying to make it so that he could hit the atom with pulses as it went through the cavity. Hitting an atom with pulses as it traverses a cavity would behave like the coin flip. And here, the idea, this is in Milburn's paper, Milburn and Travaglioni, is that what you find is that the walker spreads as square root of time, classically and ballistically with time. So the idea is that if you ask the question, if the walker is going back and forth, how long, how does the spread of the walker's position grow with time? It grows as the square root of time. That's diffusive. And this case says the walker's position grows linear in time. So if you fire a gun, bullet travels that way, it'll go, V is, D is VT, right? Distance is velocity times time. But in fact, the walker is going both ways. So you have this weird behavior where your walker is spreading linear in time, but going both directions. And this, by the way, this kind of thing is still relevant discussions in quantum biology about the photosynthesis. So a lot of the quantum biology photosynthesis articles deal exactly with that split. Okay, so these were the early implementation papers, 2002, early theory papers, 93, and about 1999. Okay, so now I need to tell you what the random walk is so you appreciate it. And this is kind of subtle, like we talk about it, it's intuitive, but now let me try to explain what a random walk is and a quantum walk. So I explained the diffusive process, Brownian motion, and it really goes down to Fourier's heat equation, which is a second order derivative in space and a first order derivative in time. And the idea is that it describes, for example, a Gaussian spreading where the width grows with the square root of time. Square root of time comes because first derivative here, second derivative of there. Now, it turns out that you can make this equivalent to a stochastic differential equation. So if I wrote dx by dt is v, you'd know that was the velocity, is the change of position and the change of time. However, for random walks, mathematically, we're able to introduce the square root of dt. And the square root of dt comes in, same as here, there's second order, first order. And actually, if you go through and you read Joseph Fourier's original work, if you study his work, Fourier actually got things wrong in his first paper by having the wrong scale on derivatives. So this idea that you have first and second derivative, it's interesting historically going through how Fourier constructed his equations. The mathematics of this was sorted out by Norbert Wiener in the middle of the 20th century. So there's very interesting mathematics on measure theory to get that right. And then over here, this is an example, like random walk, another example of a random walk behavior. And you can see, you get the feeling, this is the diffusive process. So in a way, these are dual to each other. This is showing the mathematics of diffusion in distributions. And this is showing the mathematics of diffusion as a stochastic trajectory, and then you would do it over and over and over, make a weighted sum, and get this. So these are equivalent forms of mathematics, proven to be equivalent. This is what we want to deal with quantum mechanically. So now there's actually some very nice math that comes in, but I'm not going to go into it. I'll just give you the sketch. And so the idea is that we're doing what's known as quantization. So if we take the probability distribution and quantize it, we replace it by the density matrix for the quantum walker. So there's a single particle, and then when we do that, the equivalent of this equation becomes what we call a quantum master equation. It's got the Hamiltonian evolution that makes it unitary, and then there's other terms. In this case, I'm using a Lindblad term. It takes the group dynamics and complexifies it into a semi-group dynamic, and this is the noise processes, jumps, and so on. So that's how we quantize that equation. But we can also, it turns out we can go directly from there. So if we quantize this equation, there's a transition. We can say that the walker at each run is obeying a Hamiltonian evolution. So what's interesting here is there's random numbers that are thrown away. But one way to do this is to say, no, we're not flipping a coin and then reflipping it. The coin is entangled with the particle. So if we add the coin and the walker as one closed system, we're able to then map that stochastic evolution to a unitary evolution. And that's what makes it very interesting. We can add stochasticity separately, so there are ways to generalize this. But it's very beautiful that we're able to replace the stochastic evolution by a Hamiltonian expression. And then what happens at the end is we measure the walker and we forget about the coin. So we trace over the coin and then we're able to see different behavior. So if this is the essence, is taking a stochastic equation and mapping it to a Hamiltonian evolution where there's the walker and coin degrees of freedom. And then when we do that, the Hamiltonian will generate some unitary evolution. This could be the walker state, this can be the coin state. Initially they're separable. They evolve over time, ignore whatever the coin state is, and then that essentially maps the walker to a new state. And then even in experiment, we see how this behavior, we don't look at the coin, that's the internal degree of freedom. We only look at the walker behavior, see what the walker is doing, and then the idea is that should be where we see our topological properties. Everything interesting should appear here. This is what's accessible experimentally. And the unitary evolution from the Hamiltonian, remember I said flip a coin, step right or left. So this is the flip the coin, walker stands still, and then S is a conditional shift. Heads go right, tails go left. So our unitary operator can be thought of as a product of a tensor product, coin flip, walker stationary, and then conditional shift. So that's the mathematics. Yeah.
In the state, you write walker first and then coin, and then action you write.
Correct. Yeah, I got it wrong.
So that should be.
Yeah, that's. Can I blame my student for that?
Yeah, sure.
I saw it. I didn't catch it, but you're right. Next iteration, I'll fix it. Thanks. Okay, and then that's the quantum walk. Now, because I do quantum information, a lot of times I'm not interested in a physical implementation, but I'm using these things to do algorithmic design. So there's very nice examples, even exponential speedups you can get out of quantum walks. So actually the first exponential speedup on the hypercube was done by Julia Kemp. I don't know if people know her name. She did 2 PhDs at the same time, one in France, one in Berkeley. But she then joined Renaissance. That was Simon's company. So I'm just mentioning because she did this quantum walk stuff and then she got scooped up at Renaissance. And since I'm in the Simon Center, I thought I should mention that. And now she's head of the Data Science Center at NYU, just there. So anyway, so she did the first study of an exponential speed up on these quantum walks. Okay, so the idea here is that we now want to search for a graph. So instead of the walker goes right or left, we're able to specify some arbitrary graph. And then this covers everything we might want to do. And a graph is made of vertices and edges. And then what the walker is going to do on this, the movement, if it's here, does it move here or here, is effectively encoded in the Hamiltonian. So when you write down a Hamiltonian, the Hamiltonian is exactly equivalent to an adjacency matrix that describes the edges. So it turns out that and this is important, all of quantum mechanics is all of Hamiltonian-based quantum mechanics is equivalent to just having this unitary map over graphs. So we're able to rewrite quantum mechanics in that way. And then over here, I've just written examples of cases where we have coin flips and coin flips. This is, and people doing Grover search might recognize this one. That looks like a Grover search. But essentially, we're able to do different kinds of exotic coin flips. So, you know, if the walker is here, it could go here, here, here with equal probability and in some coherent way, or it could have independent movements or whatever. So we're able to write, once we describe our coin in some operator formulation, then it can describe everything the walker wants to do. So, and once we start doing that, we can pull intuition. Like once we describe Hamiltonian evolution as a combination of coin flips and walks, it gives us some insight that is a little bit buried in other approaches.
So the graph has to be planar?
No, graph could be anything.
Something happens when it's non-planar?
Things happen, yeah. I mean, this is the point. You'll get topological. The more interesting the graph, the more you might get emergent topological behavior, right? Okay, so this is down to topology. And so I just want to say here, I won't be able to teach all of topology, but not that I know it all, but the idea is that we're interested in quantum topological materials. And we're interested in, again, my interest here is to work with experimental groups to see how much of these effects we can manifest in experiments that are as easy as possible, using cold atoms or photons or something. And so what I've done in this table is to break up into different kinds of properties. And so the quantum walks that we do are single walker, which is effectively a single particle theory. Now, to really study quantum materials, we have to have many body systems. But I've broken it up into what we can see with one particle and what we need many particles to see. Eventually, we'll go to 2 or more particles. But right now, we're still developing one particle stuff. And so there are different properties like interactions. Well, if there's only one particle, you have no interaction. This is topological order. It's important to have interactions. Ground states are non-degenerate here, degenerate there, and so on. I won't read them all. But the idea is that Chern number, we can have Chern-Simons number, topological order. So these are the things we're studying and not those. We would need multiple Walker theory, which is developed, but not in a very good shape right now, to start studying those. So these are future topics. And then, of course, the way we want to do it is to start going from single particle to do 2 particles, like, you know, in a condensed matter way, you start with many and work accordingly. We're going bottom up. We're just going to do 2, then 3, so a few body and work it out. Okay, and then the way it works in topological characterization is we start using numbers. I don't know, there should be a picture there that disappeared. So we have, oh, I hope the other picture's there. I gave it to the front desk for voting. Okay, so here there should be a picture of a, why is it not there? Now I'm getting worried. Yeah, so this is the, yeah, that should be what we see. That was the one I sent over.
It is probably converted on Windows rather than, we can plug this in directly probably. If you want.
But I don't have an adapter for that.
We can find one, I'm sure. You
Okay.
need USB-C
Well, let's see.
or...
Let's see, but, oh, other pictures are there, it's only that one missing.
there
Oh, no,
it
I
is.
can't.
Maybe.
Oh. Huh,
Quantum
okay.
effect.
Quantum effect, yeah, okay, so that's, yeah, we observed it, so it collapsed into being. Okay, yeah, so that's, this is the idea that you have the genus, you know, trivial, the donut, G equals 1, 2 holes is G equals 2. So these are the kinds of things you want to look at in topology, are shapes that can't deform into other shapes. Okay, so then we have the genus, but mathematically we start using some math. I'll just mention here, won't go into a lot. There's the Berry connection. So in fact, what I talk about later is the Walker moves around. So the Walker has a distribution, but there's a Fourier dual momentum distribution. So a lot of stuff that we'll be doing will be related to the topology, not of where the Walker is seen to be, but how fast the Walker is moving. So we'll be working in momentum space. And then we use something known as the Berry connection. So this is the momentum eigenstate. In most of what I do will be 2 dimensions, but it could, later I'll get to 3. and then we take the derivative with respect to a component of k. So that's the Berry connection, and then from there, we can start constructing the Chern number, and the Chern number is a way of essentially tracking. We can use that to figure out the winding number. There's something known as the Rudner winding number that we also use because sometimes we need, we'll do a time-dependent evolution. So if you have a time-dependent process and the unitary evolution is generated by the Hamiltonian, we can come up with a Rudner winding number. There's also Chern-Simons, so again, I'm in the Simons Center, I want to put that down, but so the Chern-Simons theory we could do if we get to 3-dimension. And so when we're interested in this kind of behavior in momentum space for the Walker, but we use these mathematical formulas to solve equations and then figure out what's going on. Okay, so now this field just opened up 2010. So it's not, 9 years ago, I would say this was the first paper that really investigated what is now the basis for the quantum walk approach to studying topological effects. So this was a work from Eugene Daimler's group at Harvard, Topological Characterization of Periodically Driven Systems. That was in Physical Review B. That's using this Rudner winding number to characterize. So they're saying we can do a periodic driving of the system, and then through that we can look stroboscopically or periodically at the system and see topological effects. And that opened the door to experiments. So this is an experiment. Eugene Daimler's group, some people here know Alain Aspar-Guzik, I already mentioned a couple times. So there's Alain Aspar-Guzik on the paper, Eugene Daimler also from Harvard, and Andrew White group at University of Queensland, experimental, and they did this photonic quantum walk stuff. So they basically took this idea, realized it as a quantum walk behavior. I'll tell you a bit of it, and they're essentially saying that they observed this. And then turned out, I won't go into it technically, but they were actually not, this paper wasn't perfect, no paper is, I guess. And then there's some work by Aspot in Hungary, who had a physical review paper that corrected a couple of misconceptions there. So if you do get that, you should get the follow-up paper by Aspot to get it right. Okay, and then what do we look for in these kinds of systems? So this is just an example. In this case, I'm doing this is a textbook. And so the textbook, I'm just showing you a famous exactly solvable model. This is the SSH model, Sushri for Heeger model. And so the idea is that we can study some sort of a zigzag, and then the zigzag has one edge, you make it a zigzag graph, one edge weight going this way, another edge weight going that way. You can see the zigzag is dotted lines here. We could write a Hamiltonian for that zigzag behavior, solve it, that's the SSH model. And then in that case, this is textbook stuff. Then we can look at energy and energy gaps. So there's here for the V equals 0. So V equals 0, you break it up into pairs, either this way or that way. And then you get your two energies with the 0 energy in between. And then we can vary the V. So the idea is in these topological systems, we can vary parameters. In this case, free is W equals 1, vary V, and then we can see like a band here, and then we can see a bifurcation. You get a degeneracy that lifts to non-degenerate. And then what I want to tell you though is when you study the states, like in these bands, the states, so this is the states spread over the whole thing. So if there's like 10 of those, there's 10 different regions, and it's all over the place. But for this part of it, we start seeing edge states. And by edge state, what I mean is this state is kind of close to that edge, and this one is close to that edge, same over here. So in a physical sense, what happens here is you have bulk states that are where I'm going to talk about a walker. So a quantum walker in this system would be spread all through it. But you'll also get contributions where the walker stays close to this side or close to that side. Those are known as edge states. That's the kind of thing that we're looking for experimentally. So we use the mathematics, Chern numbers, and so on to characterize, but when we observe in an experiment, we'll really look at, create a walker, let it evolve, and then look for edge state behavior. So that's the kind of thing I'm going to show you now, that we'll construct systems and we'll be looking for edge states. Okay, so this is the photonic quantum walk from this Nature Communications paper in 2012, Andrew White's group. And over here, this is what they're doing. They have photon pair source. Yeah.
I'm sorry, can I interrupt with a dumb question? Because I understand how you get edge states in models like Sue-Schrieffer-Heeger. What does that have to do with topology? I see the edge state as a surface property.
So does that go back, I mean, I don't think it's a dumb question, I think you're asking a hard one, but when you say topology, you mean you wouldn't see that as even a sign of topological protection?
Well, I don't see where those things occur in this model you just showed us.
You mean in the SSH model? Yeah, so you're asking me where the topology would arise in the SSH model.
Yes.
That would I can't answer that. I can see.
There's trivial examples. You can think about the boundary as the main wall between two vecua, and the fact that these vecua are very different. This vecua and this vecua very different means that it's the simplest topology possible. It's just Z2 plus minus 1.
I don't, and I'm not so familiar with the SSH model, I never done the math. So I think,
It's like one-dimensional version of that indices that's brought. You brought more complicated things from the previous slide. Okay. This is one-dimensional version of those. It's just kink. So it's sort of one.
Oh, and that's why I was asking, because it's a one-dimensional system. Sorry? Okay. Dumb question, I gave you a dumb answer, so I think we're, okay, I'll go on. We're not gonna do that model, so I was using that as an example from a textbook, but I need to go through and really study that. Okay, so this is the way that we do things. This is the way Andrew White's group did it in the first experiment related. Parametric down conversion creates a pair of photons. One is detected, so it conditionally prepares a single photon. So the idea is to claim that you're working in a quantum regime. Doing that, it just, if you know the photons are correlated, you measure here, you're guaranteed just one photon in the system. So it's claimed to be quantum simply because there's exactly one photon at a time. The photon comes through an optical system where there's a birefringent crystal that splits into two polarizations over here. And what happens, first it goes through some sort of a rotation. So sigma z is rotating in polarization, so you have your vertical and horizontal modes, vertical and horizontal polarizations. Sigma z is diagonal on the vertical and horizontal basis, so there's some rotation, Stokes vectors. And then there's a birefringent crystal that splits the two, and then another rotation and another birefringent crystal. So that sequence is this sequence, okay, polarization, rotation, and then the T is the conditional step. So your photon, vertical or horizontal, is the coin. It's an internal degree of freedom. So if it's vertical, don't step. If it's horizontal, step to the right. That's what you're seeing. And then there's another coin flip here, and that coin flip is equally likely to be heads or tails, vertical and horizontal, but a different phase relation, and then a different conditional operation, which is somehow opposite to that, and this becomes one step in the quantum walk. And then they keep going. And then they get 1, 2, 3, 4, 5, 6, 7, 8 steps or something. So they eventually get this through that evolution, and that split time, it's called a split time quantum walk. When they go through those steps, they're able to get a gapped energy spectrum. So they have some gapped system here, and they calculate the Chern numbers for ones and zeros, so it's topological. This is some representation of how the walker is behaving. H and V are the coin or the photon polarization. And so they were able to, I won't go into detail, but they're able to then show topological effects in their quantum walk, which they do by making edge states through the...
What space is that in where the Chern numbers are ones and zeros?
Oh, this is the parameters for thetas, theta 1, yeah, it's marked here. So it's theta 1 and theta 2. So they're controlling the phases for the rotation. So it's flipping the coin to heads and tails, and they're controlling the theta 1 and theta 2 parameters and getting Chern numbers split between. Okay, so that's the idea. This is then later, so this is an experiment I was involved with at the University of Science and Technology of China, and that one, this one we're claiming to see topologically protected edge states in a photonic quantum walk. So in this case, we're able to go up to 2 dimensions. I don't have the slide for the experiment, but the idea here is that we're measuring the photon, where the photon is, and we're starting to see basically edge state behavior. So we're able to make something where we have between 2 boundaries. So this is the θ1 and θ2 from before, over there, and then through some technical advances, we're able to get boundaries here. And so instead of directly talking about the Chern number, we're able to start doing experiments and seeing, we're starting to see localization of the photons along particular edges. We can control it. We're able to break it, so we have some control where we can make the edges become a little bit broken up, and we still see localization of the edges. So the idea is in the experiments is that we're an n equals 7 is 16 refers to the number of steps. So in this experiment, there's a step, next step, next step. So we go through a sequence of steps. Here we're able to push up to 25 steps in the quantum walk. And so the idea here is to start seeing the edge-like behavior going on in the system. So I won't go into a lot of details there. I'm just going to give you the overview of what's going on in that. But this is the kind of stuff going on in the photonic experiment. So
What is the difference of the top panels and
what is the difference of what?
of top panels and bottom panels? Is the emission to be reverted? So like 2 directions.
Okay, let me check. I got it.
Maybe different correlation or something.
Yeah, initial polarization state is the difference.
Oh,
Okay, let me go on. So I want to just cover the order. Like, there's a lot of detail in every experiment, but I'll just cover. We got this one next. This is done. This experiment is the PT symmetry version. So I'm going to give you an idea of how this works. This is also photonic. So I'm a co-author of this paper. This was Nature Physics last year. This was done by my former postdoc, Peng Shui, who's she did it when she was at Southeast University in Nanjing, and she's now at the Beijing Computational Science Center. And so this experiment is working with PT symmetry. And so the idea of PT symmetry is that the Hamiltonian, so it's quantum, I told you it's quantum mechanics kind of for another universe. So Hamiltonians no longer have to be Hermitian. They can be non-Hermitian, but they have to have real eigenvalues. And it turns out that you can prove an equivalence between Hamiltonians with real eigenvalues but not unitary is equivalent to the physics being PT symmetric. So parity changes the sign of momentum position, time changes sign of, was that both right? Anyways, parity time symmetric with I goes to minus I. And so we work with that kind of system, and then the way we can make it work experimentally, turns out that non-unitary evolution corresponds to a very, in the experiment would have to be a combination of amplification and attenuation going on, perfectly balanced with each other and no noise. So the
Bender discovered this?
Bender, yeah, Carl Bender.
He been here to our university.
Oh yeah, okay. Yeah, so Carl Bender was the first to propose the PT symmetric systems back in the 90s. I remember talking to him back then. He didn't have a physics model. So he did it more as a mathematical physics thing. And then the physics of the balanced amplification attenuation came out many years later.
So
And-
the second line is x to x, not to...
Yeah, no, yeah, you're right. Thank you. Yeah, that's a mistake. That's why I got confused over it. Yeah, exactly. So time symmetric shouldn't do that. But it should be PT symmetric. And then experimentally, the way we realize it is we do a balance between attenuation and amplification. And then the way we get rid of noise is a post-selection process. So in that one, there's just a process. And then what Peng and her group did is to insert a loss mechanism. So the way we do it, we're not going to amplify the light. So we just go through like L prime and L, 2 different loss processes. And then we just rescale the light. So we just use a rescaling parameter, so the lesser loss term appears mathematically equivalent to a noiseless
Was
amplification.
this C, was it theta?
C is the R theta from before, so this is taken straight from the paper. So it's the coin. C is coin, and in the other paper was the R. And then, so we just go through that kind of process for about 25 steps. And by alternating losses and normalizing the output, we're able to simulate the PT symmetric universe. That's the idea. And then we do that, the churn number in these kinds of topological characterizations are no longer applicable. So when you start looking at the topological system, if you're Hamiltonian, if you think of energy spectrum and gaps and all that kind of stuff, once we make the Hamiltonian not Hermitian, we have to be careful in these kinds of numbers. So these experiments and other ones I'm involved with involve theoretical collaborators who are modifying the topological characterizations mathematically to adapt to the PT symmetric system. So it's a theory experiment collaboration to get the numbers right. Oh, on time to appear, isn't that fine? Okay, and then over here, the idea is, and again, I won't go into details, kind of an overview, but we then have to go through for a non-Hermitian system. So in Hermitian systems, we have real energy spectrum. Non-Hermitian, we have real and complex. So we have to be able to generalize the energy spectrum. And then...
What's H of K?
H of K is the Hamiltonian as a function of the K vector. In this case, it's in one dimension with periodic time. And then, so K is now complex. So, and then we take the determinant, the log of the determinant, derivative, and then we have a winding number. And so that winding number is constructed to characterize topological effects for a PT symmetric system. And as I said, then we apply that winding number to see the topological effects in that system. Okay, now I'm going to tell you the open part. I don't have much time left. And I said I'm going to tell you where we're stuck. So I just want to tell you, like when you go back to here, the idea is that everything splits in two and there's polarization. So here we're experimentally able to work beyond two-level system, three-level system, etc. And I'll tell you why in a moment. But what I want to get at is this is where I want to go in the future on this. And there's a lot of theory that a lot of theory needed that I can't find, and so that's one reason I'm glad to be here. So the idea is that I want to go to what I'm going to call spin to color, and I'll tell you why it's spin to color. So polarization is like the spin of the photon, and then if you start thinking of quarks with SU3, it's color. So I'm just using the word color because that's what we call it when we go from 2 to 3. And then so this is this tells us about SU2, Cartan operator, raising and lowering operators. And then this is equivalent diagram for SU3. So in a three-level system, you have raising, lowering operator, another raising, lowering, another raising, lowering operator. Takes you through the various levels. And then we're able to extend. And so this is like a spin 1 system, spin 1, spin 0, spin -1. And then this would be an example of a diagram where you allow SU3. This kind of stuff comes up in particle physics. Okay.
What is the red color?
The red one is, that's our initial point. So in some of the stuff I've done, we've written algorithms that will, we have to do quantum walks through these things sometimes to start building up. Basically, when you build up your mathematical descriptions, the Wigner matrices, your spin matrices. Okay, I won't go into it. There's a way, we have an algorithm where we can build up our SUN matrices. And so the red just indicates a starting point. Okay, now I'm going to tell you why it comes up in the experiment that we've done in Shanghai, and that I'm trying to figure out how to deal with it. So essentially what we have is atoms in a lattice. And so I'll show you a better experimental diagram in a moment. But we're able to trap rubidium-87 atoms in an optical lattice. So they live in the optical lattice. Each atom is driven by a Raman transition. So we have 2 ground states in the hyperfine manifold, Raman transition that we detune a bit. And so this becomes our coin, 2 different states. And it's a synthetic spin-orbit coupling. So you use your mathematics for spin-orbit coupling, we're able to see all the stuff here. Write it mathematically, and we get almost perfect agreement between the theoretical description and the experiment. And so what's happening is you have a bunch of atoms, and they just wander around the system, but through this kind of coupling, you get topological effects because it can wander like this or that, and we can start creating parameter variation in the system. So this is the kind of system we have, and then even though there's many atoms, each atom it's translationally invariant, so you can pretend there's just one atom doing a walk. And then we care about momentum, so after the experiment is done, we don't look at where the atom is, we measure how fast it's going. These are time of flight experiments. Okay, and when we do it, we can write down the mathematics for it. So this is the synthetic spin-orbit coupling, and essentially the atom is set up so it has some probability of staying where it is, something that moves it to the right, something that moves it up, and then we have our Hamiltonian, and we describe it in some fashion, and then this is the hopping terms. So we have hopping terms going on, and we're able to write this Hamiltonian, do the experiment, and see agreement. Okay, when we start doing that, we can then look at the position distribution of the Walker. This is very characteristic of a quantum walk. Remember I told you the Walker moves ballistically in two directions? So you see a ballistic movement to here, a ballistic movement to here, a drop in the middle. Whereas with the Walker distribution,
Why it's not symmetric? I mean,
because it depends on the initial coin state. Yeah. So if you reverse the coin state, it would be the opposite.
Thank you.
And yeah, okay, good. And then we're able to do things, and then we can play with the parameters, and we can start seeing some effect where the Walker has a high probability of staying where it is, some probability that it moves a little bit, like square root of t, and some other one. So we can play with parameters to interpolate between quantum and random walk behavior in the system. And when we do that, we found something we thought was interesting. So this article we wrote, it was a theory paper, it was on Physical Review Letters a couple years ago.
I'm sorry, do you have any randomness in your system, or it's just
Purely
transition?
Hamiltonian generated unitary evolution. In our theoretical description, the experiment is very, very, very close to unitary. Then what we do, we just study the Walker motion. So in this case, physically, we look at the Walker motion. This is the rate of change of the spread with respect to T2, which is one of the hopping terms. And we found some sort of indication of phase transition. So it turns out that the spreading of the Walker, depending on that term, will have a point of inflection at certain points. And whether it has points of inflection or not, turn out to be exactly correlated to our calculation of the Chern number.
What's E capital?
I'm sorry?
E capital of K, what is this?
EK is the energy spectrum for the Hamiltonian. We write the synthetic spin-orbit coupling, diagonalize to get the energy, and find it as a function of two-dimensional momentum. And then that's the quantity that we're plotting over here. And then the Hamiltonian that generates it has those hopping terms. So we take the derivative there, and then that's where we find these kinks. So we find that these points of inflection for some, nobody ever saw that before, it seems very new, but these points of inflection in the Walker behavior are telling us something about, there's some sort of vortex behavior forming, and these are telling us something. Okay, I won't go into detail. I want to get to the.
Is there a classical analog to this equation?
Not that I know of. Never seen it before. We got it by accident because we just started looking at the behavior of the Walker, just plotting it, and then we started seeing things grow and slow down, and then we just tried different things to understand. So we couldn't find anything anybody said that hinted at it.
Which parameter is T2?
T2 is, I think it's this one. So we could have done it with TX. We also see the kink with respect to the other parameter. But we allowed these to be different, we're just varying that.
It's anisotropic.
Pardon me?
It's anisotropic, of course.
Yeah, we're allowing, our Hamiltonian allows free changes between them. Okay, so then we could do our energy band dynamics in the system. So this is really just studying as a function of Kx and Ky. We're just studying the energy gap in the system.
I'm sorry, I forgot. What's M small?
M is the equivalent to the term T0.
Thank you.
So it's staying in the same place. And then this is where this is the phase transition. When you start getting your energy gap disappears at some point, that's the, I think a lot of people know that that's the point where we get the transition between two topological phases. Okay, effective Hamiltonian here. That describes the system. So this is all the synthetic spin-orbit coupling. Okay, then there's the experiment, the way we do it. So this is the experiment in Shanghai. We trap the rubidium atoms in the system. We have Raman terms driving it. And then what happens is we create a potential well. that holds the system together, and then we drop the potential well, and then we measure time of flight. So we just wait a while, then do an image of the atoms as they fly apart, and then that gives us an experimental measure of the momentum distribution. So when you see these kinds of pictures, we're able to get them physically directly from the experiment. Okay, so...
the critical point was about the right predicted.
Pardon me?
The critical point was
Yeah,
predicted.
well, so the point here, this kind of stuff we can't see directly because the experiment imaging is not able to get down to single lattice sight level. So it's kind of like looking at things a little blurred. So it's too blurred to see these kinks are not observable yet because we don't have the resolution. The technology is not there yet to make an optical lattice that can be resolved site to site. But we are able to do time of flight. So these kinds of things we can see. And they appear in diagrams here that I won't go into, but basically we're able to do these kinds of diagrams by varying parameters, and these are experimental measurements, and these are vortices forming in the momentum space. So whether these vortices form here, these are two different topological phases. But this is the point I want to tell you. So these are the hyperfine levels, but we have some detuning. We're getting contribution from higher levels. If we didn't get those, as our theory works, then the internal degree of freedom is a two-sided coin. But we will get some contribution from these higher levels. Our theory doesn't account for that. But in our experiment, we can get effects. So again, I'll just, we'll get effects coming in where we're able to measure things here, and we're able to see things and model it, and we get deviations between our theory and experiment. And the deviations we're getting, we believe, are not due to experimental error. We're not sure yet, but they could be due to higher order spins contributing to the topological phases. So this is what I think is really exciting, is we have to start separating and looking at spin one behavior. So the idea, these are diagrams and what we look for and the kind of agreement between theory and experiment. It's almost perfect, and we'll get small deviations I won't go into. But this is the point I want to end on, is that what we're now doing is, we're now starting to reconstruct the Hamiltonian where the internal degree of freedom can now be spin one. And we're also constructing, so these are like 3-level atoms living at every site. And then what we're able to do is to write, instead of SU2 describing the coin, we're able to go to SU3 dynamics. And so we just write down the SU3 dynamics that is determined by atomic physics principles, and then we're starting to try to explore where we will see effects. Okay, so now we're not that smart. So we're doing dumb things like saying we found a kink before, can we find a kink? We look for topological phases, and we get very boring diagrams. Here we don't get our kinks, although every diagram we do produces some sort of a kink in that distribution, but we're lost. And so the idea of being lost, we write this Hamiltonian. We're trying to calculate various quantities to look for behavior, like these kinks. And so we think we have the experimental data at hand to show us topological effects that have a coin with SU3 symmetry, and we don't know how to do the
Each of
mathematics.
K is your Hamiltonian, correct?
Yeah, this is the Hamiltonian, these are momentum, and this is for 3 levels. So what we're doing here is before, like we do these Raman transition, and then we say that detuning is big enough, we ignore it. So it becomes a 2-level system where the coin flip is really between these levels. But now we can initially control the detuning so we can get a perturbative effect that's a 3-level system. And we can control these parameters. So we would be dominated by that, but our perturbative corrections would be due to going from SU2 to SU3. You see? And then in going from that, we've been picking up the very few theory papers on this and trying to figure out how can we account for these kinds of effects. Initially, what we're playing with is just SU2, but spin 1. So, and this is what we talked about over lunch, some of the stuff. So the idea of going to, this. So our atomic lattice, initially we analyzed everything as 2-level systems. We can analyze it as 3-level systems. We can initially just do SU2, control the parameters to do spin 1 behavior, and then we have a 2-dimensional lattice of spin 1. So we talked, some of us at lunch, we talked about a 1-dimensional line that's spin 1, but we're able to make a 2-dimensional lattice of spin 1 particles. And then we want to be able to do this, and like the atoms will hop around, okay? The terms will then be driven by, in that case, SU2 spin 1 type dynamics. We're able to do the experiment. We need to know how to look for the signatures that would be topological phase transitions. And that's what I've been stuck on for about a year. And that's kind of a good ending for the talk, because I'm pointing out where I'm stuck.
Any questions?
I have one very basic question. What is the difference of this with just band theory of tight binding model? Basically, we're studying just tight binding model with one particle.
Yeah, it's the same thing. So there's the rest thing I had at the beginning. So like when I tell you this, it's not like you have to go and read quantum walks. You'll just discover it's another language. So the idea when we're doing the tight binding, just go back to the beginning point. It's what I said here, like, you know, that we have diffusion, we have stochasticity, and we have a way of turning into quantum walks. So the real idea here is not that it's different, it's that the quantum walks just give us another way of writing solutions to single particle systems. And then all the tight binding stuff this is just another language. So the only advantage of doing the quantum walks, it's allowing us to see many different things under one framework. But if you are used to tight binding type calculations, you could look at all the quantum mechanics in the same way. So you could take Schrödinger's equation for, you know, particle in some nice potential, and then break it up in a lattice and also look at that way. So,
But then, sorry, I continue. So
Please.
then in tight binding models and in solid state physics, the topology is characterization of a band, of the whole band, not just one particular state. There is no topology associated with a given K state, for example. It's just the whole band is characterized. So when you do quantum walk, you kind of cover all states because you start with initial delta function.
correct.
Right? So you cover that. But you don't necessarily cover them uniformly, or in the process of the walk it can change. So the question is how you go from your initial state plus quantum motion to the band topology. So how you connect these two things? You're using Chern number. Chern number is for field band, for the whole band of the tight binding model.
Right.
While you are dealing with just individual trajectory, quantum trajectory.
Well, so like when I start with the initial localized state, would you agree that that's equivalent to a quantum quench?
Sure, yeah.
Okay. Would you have the same criticism for a quantum quench?
No, I'm just saying that
Okay.
you obviously have your band with non-trivial topology at your disposal.
Yeah.
So, but I just try to see what's the connection between the initial state. Suppose that they start not with delta function, but with something a little bit spread.
Right. Then it will
Will
help.
I just lose all these kinks and everything
Yeah. Right.
immediately or not immediately? So how?
Yeah. Well, if you don't start with a delta function, then you could start with like a superposition of different positions or a mixture of different positions. So if it's it'll be slightly different in both cases. But yeah, if you have
For example, if I start with a plane wave at given k, I will not see topology of the
Correct.
band at all.
Yeah, so it's important that we start with a localized state. So we have an atom at some point, and then when it evolves, the localized state has a flat spectrum under a Fourier transformation. And so that way we're exploring the full K-space, is how we look at it. But if we don't have a perfect preparation, then we sacrifice. So I'm not sure exactly what you're getting at, but you might be talking about some of the imperfections we see. Is that the idea? That it's not perfectly localized at the beginning?
No, I'm just to not understand how you get the full topology in your quantum walk problem because it's just one state.
Well, what we do, so we start with the initial localized state, and then it evolves. Then we make our lattice disappear. Then we look at time of flight measurements for the atoms. So then we have, we measure we do a spin selective measurement of the atoms flying out. So we're able to get the K-space picture for both spin up and spin down.
Okay, so yeah.
And that's the kind of picture.
So can you extract your number from results of this type of flight experiment directly?
Yeah, these are the kinds of things. So the blue and the red refer to whether it's, say, spin up or spin down.
Is it very curvature or what is this blue red?
These are just raw plots, like you can see the gamma points and all these, solid state physics.
Yeah.
So these are the,
What color?
How much
What
the
color?
band is occupied? This is how much the particle occupies the band.
I'm not sure I get it, but this is like K-space. And then the blue or the red are spin selective measurements of the atoms. And so these then become,
So this is just spin projection up and down? This is
yeah, it's
blue
the
red?
amplitude of the wave function. Say spin up is blue and red is spin down. And then that's just, and it's normalized. And so that tells us the probability. So we see a high probability of, say, spin up with those values of K, and a high probability of spin down with those values of K in one phase. And
Can you compute Chern number from this picture?
yes, so we write down the Hamiltonian, and then we do our Chern number calculations.
No, you definitely can compute Chern number from Hamiltonian, but from experiment,
Yes.
can you do some processing of your data
Yes.
to get Chern number?
Yes, that's what we do. So then we get, these are the experimental type points that we get. So we will calculate, we'll take the data and then infer using sampling techniques, sample to get the Chern number.
Yeah, I'll ask more.
Okay, more questions? Okay, I will dare to ask you a question of high level. We teach our students, or they teach us, when we talk about topological quantum computers, on a line of keywords that starts with the fractional Hall effect, onions, creation, and then trading. So you haven't used any of these keywords. So what is the connection that they can make, or we can make, of this topological quantum walk and the braiding theory?
Well, so in this case, we're just making a list of things that are topological protected. I don't know. Well, okay. So how do we?
There's no anion in the model.
Yeah.
There are no anion.
No anyons.
So there's no braiding.
There's no braiding
Yeah.
because we don't have two particles either.
Right.
So I mean, I guess part of what you're asking, like, if there's value in the quantum walk description, there could, I'm not sure with anyons, but there could be a quantum walk way of describing the same thing. And then it's a question of whether it's more or less useful to use that language. So,
Yeah, so where is it going?
It's useful by itself for growth research. There's generalization of growth research for structured database, and we don't need any anions. Just quantum walk will accelerate growth research.
Yeah,
That's
but
direct application.
but I think the question is more what comes out of the framework that I just
Right.
presented
Yeah.
that impinges on the educational system with fractional quantum Hall effect, et cetera. And I think I don't know the answer yet. Like at the moment, we're still using this framework to design experiments to start tackling some of the topological effects. The map is then to go to two particles to do it. And the kind of things that we're proposing seem to be clearer in this framework than the other. So I don't have a better answer.
So it might converge in future to the same line of development
Might.
of intellect. Yeah.
I have a question on the PD symmetric part. The PD symmetric part.
Yeah.
Is it easy to see that it's PD symmetric in the experimental setup? How do I?
Is it easy to see?
Yeah.
You first have to appreciate that.
Where is
Like-
the P with T part?
Okay. It's not. There's a sequence of steps you go through. So you first write. This is Carl Bander's approach. You kind of write down the rule for PT symmetric. So you have your PT symmetry. Then you get this rule about non-Hermitian Hamiltonians with real eigenvalues. And then when you go through that, then you're asking if it's easy to see from that.
So maybe more specific. What is the Hamiltonian in this case? Or
Oh.
because you were talking about process, it's not.
Okay, so let me just go back a step. So first, without PT symmetry, if we take a unitary evolution, we know it's by Stone's theorem of mathematical physics, we know it's generated by Hamiltonian. In this case, there's a sequence of 4 steps. So, and generally, as I said, there's a conditional step for the Walker. I won't show it, but so we do this. Then you know from Stone's theorem there has to be a Hamiltonian that generates that. If we start writing that, then we get this synthetic spin over couple. So we don't write it, but it turns out that this is equivalent to just using some Hamiltonian description. But by doing quantum walk description, it helps us see how to do it experimentally for the systems we know. And then, the PT symmetric will have the same thing. So we have a sequence of polarization rotations, conditional shifts, and 2 different loss terms.
So it's like a dissipated part that you have.
Yeah, and then you
The
can.
first piece is just unitary, right? So the
This-
before loss part.
Yeah, this is unitary. This is loss, unitary, different loss. Then it's back to the original. So it alternates the losses. And then if you normalize it, then the smaller losses look like noiseless gain.
So it's like a post-selected scheme?
Correct.
Okay.
That's another way to think of it. And then what we do, when we combine this effective amplification attenuation, then when you have that sequence of operations, you just take the logarithm of your unitary, logarithm of your non-unitary evolution, and that will give you a non-Hermitian Hamiltonian.
Okay, if no more questions, Eric, thank you very much for this talk. And please always give us the talks for the first time. That's the beauty we can absorb.
Okay, yeah, thanks.
Thank you.